So my idea today is to talk about wearable computing and its machine learning applications. So it's a quite broad topic. I will not go into details. I'll mention a lot of things, but I will not go into details. So it will be kind of overview of the landscape of the wearable computing and its machine learning applications. Okay, so most of the studies that I will talk about today, I've been personally involved in. There are a few that I'll mention which are done by others. So I'll first start with the wearable computing. What is wearable computing? What is machine learning? Briefly. Then most of my talk will be on activity recognition, and you will see why it is so important. Then I'll talk about fall detection, energy expenditure estimation, and I'll finish with recognizing arousal, stress, valence, facial expressions, and similar. So let's first put the wearable computing context. So we have, let's say, well-established research areas such as artificial intelligence, sensing, human-computer interaction, mobile, and distributed computing. Of course, they interconnect. It's not like they're on a separate island. But then we have one area which is called ambient intelligence. But this kind of title, ambient intelligence, never got its attention. So it's not that popular in the research community. Ubiquitous computing, on the other side, it's much more popular, and it's more used in the research community, and it's kind of similar to ambient intelligence. Even more pervasive computing is another term that is very often used when we're talking about sensors, artificial intelligence, human-computer interaction, and similar. And on top of it, I would say it's the wearable computing. So wearable, the name itself says wearable devices. So the basis or the input source for wearable computing are wearable devices which are recording something with their sensors. So all these devices that you can see on the slide, smartphone is a typical and probably the most commonly used device for wearable computing. Smartwatch is quite popular. So smart wristbands, smart rings, or similar. So what makes all these devices smart when we say smartphone or smartwatch and similar? The things that make these devices smart are actually their sensors. So they have a lot of sensors. On this slide, you can see on the top a typical smartphone that we all have in our pockets or on our desks. It has dozens of different sensors. It can measure lots of different things, but the sensor data usually looks like this graph on the right. So this is an accelerometer sensor, and I'll talk a lot about accelerometer sensor. But this signal by itself, it is not that informative. So this raw sensor data, has to be somehow transformed into some meaningful data that can provide some service potentially to the user. That's the final goal, to ease our lives, right? So, for example, we are all aware that the smartphone recognizes activities. How does the smartphone recognizes these activities? One of the sensors that is usually used for activity recognition is accelerometer. So out of this data, out of this raw sensor data, time series data, how to extract that, I don't know, this is walking, for example. So during this presentation, I hope that you will learn how to do it, or not learn, but at least you will be aware how it's usually done. Yeah, my assumption was that there will be people that will not know what is machine learning. So 1 minute about machine learning. Most famous and successful field of the artificial intelligence area. So the point with machine learning is how to learn from data, from lots of data, how to identify some patterns which are difficult to identify by a human. So, and the final goal is to extract this useful, interesting knowledge, which is not known before. So the model should be valid, should be novel, should be useful, and to some extent, let's say, understandable. So at least to understand the decisions that, I don't know, it says this kind of activity or that kind of activity. So the idea is how to create these machine learning models out of data. So this table that you will see here is the basis of for machine learning, for supervised, let's say, machine learning. Here, this is a typical table that I'm usually using, or we are usually using when we are teaching students about machine learning. So you have actually, it's a simple table, which is an input to a machine learning model, to machine learning algorithm that will learn a model out of this table. So this is, I don't know, a bank loan application example. The final column, for example, is the class. Should the bank give loan to the user or not? All these here are called features or characteristics of in this case, the user. And these features are actually where this machine learning field gets interested, or where good machine learning engineers will be better compared to others. These features are usually not given. So you should be able, as an expert and machine learning engineer, to find and extract these most useful features regarding your problem. So domain expertise is usually also needed in this process, feature extraction process. Once you have this table, it's easy. So it's super easy. You will find, you will use Python library, a scikit-learn or whatever, and you will say, okay, this is the data, please learn a model, and in a few seconds you will have a machine learning model. Then, of course, you will evaluate, you will draw some graphs, you will investigate the errors, but this table is really the basis of a machine learning model. At the end of the day, the model can be as simple as this here. So here, all the skeptics about machine learning will say, yeah, if it's if then else rules. If they are simple enough, you do not need machine learning. But usually they are so complex, so you need machine learning to find those patterns. Okay, let's continue with the activity recognition. So I'll talk about classical machine learning approach, how to get this table, famous table that I mentioned earlier, some hybrid machine learning approaches, deep learning approaches, some challenges, and at the end I'll talk about some interesting applications about eating detection and SHL transportation dataset. So activity recognition, the idea is to recognize the activities of the user, of the person, right? So we have the smartphone that recognizes the activity. It's a known phenomenon. So to recognize that, I don't know, during the day today, I was walking for 1 hour, which is great if I'm doing that. And then, I don't know, I was sleeping for 8 hours, then I was sitting for usually 8 hours or whatever. So to recognize the daily activities. So how to do it? How can a wristband or a smartwatch or a smartphone recognize these activities? Usually, it's a machine learning model that uses accelerometer data. Accelerometer is a sensor which is very famous these days, and you cannot find us. Most of the smart devices that we usually, or these wearable devices that we're using, have accelerometer inside. So the phone even has 2 or 3 accelerometers inside. Each of them dedicated for something. One of them is for recognizing activities, movements, and similar. So the accelerometer is actually the sensor that recognizes when the orientation of your phone. So when you want to rotate the picture that you took in a landscape or similar, then this is the accelerometer that is recognizing the acceleration. So in this case, it recognizes where is the Earth's gravity. So when you rotate the phone, it will detect, and then you can create a simple if-then-else rules at the end, which will say, aha, now the phone is the phone is in a landscape mode, for example. So it measures the device's accelerations, also the gravity of the Earth. And this allows, for example, this is a typical signal that you will see from accelerometer. So you can see a walking, so quite a lot of movements, some going down or a transition, and then lying. As you can see, it's still lying. And the z-axis, for example, here has the gravity of the gravitational component. So as you can see, it's a trigonometry, it's a linear algebra. So if you have a good basis with linear algebra, you can easily work and play with this kind of data. So the idea is how from this signal here to recognize that, I don't know, the first 10 seconds are walking, then transition, and then the next 10 seconds are lying. Okay, so this shows a classical machine learning pipeline for activity recognition. So we have the data set. So data collection for activity recognition and also for wearable computing is a problem by itself. So I'll explain later how do we collect data. But the idea is you collect data and somehow it is annotated. I don't know, that the person is walking here, transition down, sitting, do you see my mouse movement of the mouse cursor?
Yes.
Okay, great. So this is input to the machine learning pipeline. So usually there is a data pre-processing, some filtering done on this signal. Then you usually segment the data on, I don't know, 1 second or 2 second intervals. And on these seconds, you extract features. So you extract, let's say, hundreds of features. We'll see what kind of features. And then you put them in a machine learning model, and this classification model actually will recognize the activity. So every second, it can recognize the activity, or every 2 seconds, it can recognize the activity. So this is a typical machine learning pipeline. I'll go through the steps one by one. Yeah, data collection. So this is me wearing, I don't know, this was 10 years ago or something like that at the Joseph Stefan Institute, where I did my master's and PhD, wearing this super wiry equipment of accelerometers. So this was 10 years ago. These Bluetooth wireless sensors were not that popular. So these yellow marks are different accelerometers, and I was performing some activities in this room, which was my office for the first 2 years. And there was another person sitting here, which was clicking, okay, now the person is walking, now the person is sitting, now the person is lying. And these were the annotations. And this is not perfect, but it's good enough. So on the transitions, you might miss a little bit, but in general, you will collect a good data set. Okay, so the segmentation part. This is a slide that I teach my students about some sensor data. So there is a quiz question here, but I'll not ask. So this is, for example, non-overlapping sliding window. And on the right side, you can see an overlapping sliding window. So for example, it's a parameter. You choose how big this window should be. For example, 1 second. And in this 1 second, you take this 1 second of data, which is, I don't know, 50 data samples or 100 data samples. It depends on the sampling frequency. And you calculate features out of this window. So each window is a feature vector. So what kind of features? For example, you can imagine that the red lines are the window, right? So you can calculate the mean value of the acceleration, the standard deviation, the root mean square, and lots of different statistical features. Actually, today you have a lot of libraries that can extract this kind of features. TS-Fresh, for example, is one of them. You just give a segment and it gives you back hundreds of different features. And at the end, you end up with this kind of feature vectors, this famous machine learning table. Once you get this table, then it's easy, or let's say it's more interesting to play with different machine learning algorithms. And then you generate this kind of graphs that, I don't know, show different comparisons. So where you discuss your results and similar. So the trick is how to end up with a good feature vector table. So for example, this is one of my first studies that I did for activity recognition, and each of these bars actually shows different sensor combinations. So as I showed you, we have 6 different sensors. So for example, thigh left, thigh right, ankle left, chest, ankle right, waist. And as you can see, if you use them individually, that the waist is the best performing. If you combine them by 2, then the chest and the thigh left is the best performing, and so on. So the idea of this graph is how to combine which combinations are better and similar. So this was one of the early studies that we did in 2010, and it was published in 2011. And this paper actually has quite a good number of citations, which is interesting. So my first conference paper has the most citations of all of my papers. And it is a first one, so it's not a great one, but it tells a nice story. Then this kind of graphs are also quite commonly used in activity recognition. So each of the activities, how good is recognized. So this will be the recall value for each of the activities. So you can see lying activities is quite good recognized. Standing, going down is not that good. Sit on the ground is 50-50. So these smaller ones, transitions, which do not have a lot of instances, are not that well recognized. Another important thing here is that usually when you evaluate activity recognition model, you use this famous technique, leave one person out. So what does that mean? That means that if you have 10 people, data collected from 10 people. So 10 people were walking around and you were recording data. When you train the model, you actually train on the 9 and you test on the 10th. And then you repeat this process for each of the people. So each person is in the test data only once. And then you report the average at the end. So why is this needed? Because you imagine that your model that you will create will be used in practice. For example, in Apple Watch, for example, you work for Apple, you create the activity recognition model, but this model will be tested or evaluated, not tested, but evaluated in practice by people which are not in the trained data. So this is fair technique how to evaluate your data. Then we did this, at the bottom you will see, usually a reference to the study that is doing. So this is one of our studies done in 2015, where we collected really huge data. I mean, we analyzed 3 labeled data sets, GSI, Faculty of Sports and Opportunity, and 1 real life study. This real life is a problem because we do not have the labels, but here we can report what is the accuracy or F1 score or whatever. And actually we analyzed, 169 million data samples, which is around 3 million data instances. And it was a good training for us to do this exercise in this paper. So this is one of the results that we got. So which sensor location is the best and which of the machine learning models is the best. So here you can see that the random forest outperforms clearly all of the rest. And also the belt was quite nice. The tie left, this is actually left pocket in a trousers. The ankle is also left. And also the left side was better compared to the right because most of the people were right-handed. So less movements, more accurate predictions, that kind of, especially for the static activities. Then we did another study, which was before the one with that I showed earlier. So it's not chronological. We wanted to participate in a machine learning competition. It was activity recognition competition, and we had this model which was, working quite good. But because it's machine learning, it's random forest. So random forest, to be honest, is killer in activity recognition and this kind of sensor classification data. So ensembles, random forest is usually really good. Super heavy deep learning can sometimes even perform poorer compared to simple random forest. So random forest was quite good. near perfect accuracy. Don't look at this accuracy. It's really high. It depends on the data set that you have. So for this competition, we had really clean and nicely collected data set. But we said we are not sure how it will behave at the competition. So we said, okay, let's incorporate some expert rules, which are again some features that we believe we understand and we are incorporating in some if-then rules. So it was a combination between expert rules and machine learning. This data mining is used because the conference was data mining conference. So machine learning and expert rules. And this is the architecture that we created. So it was several random forest, two random forest algorithms. So the first one recognized cycling and other. Then actually what we wanted to achieve was to create rules for this simple and not dynamic activities. So when you're lying, you're still. When you're sitting, you're still. When you're bending, also you're kind of still. So we described these features using some angles in the acceleration. And then at the end, we had walking and standing. And this improved the results a little bit, but it was not that improved for, I don't know, 0.5 percentage points. The advantage was that we better understood what will happen here, especially in this part here. And we actually won this activity recognition competition. So this was our first validation that what we are doing at the Jožef Stefan Institute is quite good, top level. So this was back in 2013, if I'm not mistaken, and we achieved really good results compared to the other competitors and also compared to the previous year's competition. Actually, this is the equipment. So it's only 2 sensors that we gave to this lady here, and she was wearing the equipment and performing different activities in this apartment, and our system was recognizing that in real time. Then I'll go to the next. I mean, once you have this baseline, you're kind of this architecture here. It looks kind of complex, but it's not something that we just came up in a few days or whatever. It was a lot of testing and trial and error. So this was architecture developed by all these people here. And the idea was to create a model that will recognize activities from glasses, so from head movements. And these were the activities here. So as you can see, they're quite similar. For example, you have sitting on a sofa using smartphone, chair, stationary. So these are all sittings. So we created a traditional pipeline and it didn't work, or it worked like somewhere 50% F1 score. But then we started to improve the pipeline. So we said, okay, can we analyze and compare the signal, the raw signal using dynamic time warping? Can we incorporate also k-nearest neighbors here? So we tested lots of different ideas, and this is the final one that gave us around 67% F1 score. So it's an ensemble and voting scheme. And actually we won this competition, and we won another one at the same year. So this was our lucky year in 2019. This one is with the head movement, and this one was different. I think it had around 6 or 7 accelerometers. And what I'm really proud of is that in both of these studies, students of mine at the Faculty of Electrical Engineering and Information Technologies were part of it. They were building the ideas. They were developing the algorithms, which was amazing success, especially for undergrad students. Now, the next question that comes to mind when we talk about machine learning. So nowadays, it's impossible to publish something about machine learning if it's not deep learning, or at least to show that deep learning does not work and to show experimentally. So it is similar case also in activity recognition. But I'll be honest with you, random forest is really good. Random forest on good features, experienced people that work with activity recognition is really difficult to beat. Of course, deep learning, it's much more powerful, right? And you can always, in a way, overfit, and you can show better results. But if you give me two models, deep learning and random forest, and if the deep learning is slightly better, I'll always go for the random forest. Because with deep learning, as I said, they are more prone to overfitting, especially if you have the data set, the whole data set at your at disposal. So you should be really, really careful. So we also tried back in 2016 some deep learning with convolutional neural networks and LSTM. So the idea is how to substitute all these steps with deep learning. So it is in theory, yes, in practice, no. So still you have segmentation, still you have data pre-processing, feature extraction, maybe not. But if you have feature extraction, then maybe you do not need deep learning. So the idea with deep learning is also to learn some features automatically. So these are the initial results that we got. So this is a conference, a workshop paper. So it was not like some journal that we investigate a lot, but it showed that, yeah, deep learning has a potential, convolutional neural networks. Since then, I mean, deep learning improved a lot, but as you can see here, you will get some activities with zero. And this is not the case when you have random forest. In a way, it's more robust. Or this one with 8 percentage points. So in 2016, this is one of the really early papers that showed the real potential of deep learning. So this paper is published by Francisco and Rogan. It's deep convolutional and LSTM recurrent neural network. So conv-LSTM network. So this is the architecture that they proposed, and they showed that it works really well. So nowadays, people, when they do activity recognition, they use this kind of architectures, or at least for comparison. This is also a nice study where it was shown how it is better to combine the convolutions, because here you have 3 time series. Do you analyze each of the series with a separate convolution as a separate to apply separate convolutions? Do you combine them as they are here, or do you combine multiple sensors? So this is a nice study that showed that sensor-specific normalization is needed. Hybrid fusion better than early fusion. So those kinds of lessons were learned from this paper. Okay, what are the main challenges in activity recognition using accelerometers? So all the models rely a lot on the rotation and orientation of the sensor. So if you, for example, if this is the sensor, if I collected in the data set, if the person was wearing the sensor like this, but then I have another person where the sensor is rotated a little bit, that's completely different data, and the model will fail. So this is a huge problem. So you have to assume perfect rotation and orientation of the sensor when used in practice, which is impossible. So we kind of proposed a partial solution to this one using some rotation matrices. I have a slide over this. I'll show it in a few seconds. Then this is also aligned with the previous sensor-dependent model. So my model is developed on one accelerometer, but what to do on another accelerometer. So it depends how detailed you want to go. So for example, how the Google activity recognition works, it is not relying too much on seconds of data. So it's more like in this hour you were walking for this much, or in this hour you were driving your car for this much. And also the GPS sensor is used in that case. But once you go deep into the accelerometer, this can be a problem. One kind of accelerometer, another kind of accelerometer. Potential solution here is, I don't know, train a supermodel and then apply transfer learning or multitask learning. then unknown number of activities. So you can say my model recognizes 10 activities and it's trained on 10 activities, but in theory, you can have new activities which are not in the training data. Then what do you do with this kind of activity? I'll show one study that we did with unsupervised activity discovery. Lots of individual studies, lots of models. Can we create one general model for human activity recognition? We are working with one student of mine, or partially mine, on this kind of idea, but it's taking time. So to create an image similar to the ImageNet models that we have, deep learning models for images. Data collection, data augmentation is a problem by itself. So I'm not sure if Orhan is here, but he has a nice idea about how to use virtual simulations. So in 3D software to create a human and then perform different activities in the virtual simulation, and then use that data, somehow extract the acceleration data to train the models. Okay, I will not go into details, but this is the problem that I explained. So this is a, let's say, perfect vertical orientation of the sensor. But what if the orientation in real life, when the person is sitting, is like this? So you can use rotation matrices, which are quite known in linear algebra. So we applied that one. It kind of worked automatically in real time. And we got real improvement from, I don't know, for the sitting activity from 28 to 18. Then the transfer learning is really huge, and I'm really optimistic about this study. Stefan Kalabakov, which is currently at Jožo Stefan Institute, is working on this one. How to combine different data sets, how to create this supermodel that can be applied on different data sets. So imagine you have a model trained on 10 data sets, and then you use that model on your data set, which is a small data set. So typical transfer learning scenario. We have some initial results in Informatica. He's currently preparing his master thesis on this one, so it's an interesting study. Also, we developed this data augmentation technique, which is explained in this paper here. So in the data set, you have let's say the perfect orientation, but you can using rotation matrices, rotate the sensor, not physically, but in data set manner. So rotate the sensor by 1 degree left and right, 2 degrees, 4 degrees, 5 degrees, and this way to augment your data set and create more robust model. Unsupervised activity discovery. This was part of my postdoc at UK together with Rogan. We created this temporal clustering, online clustering algorithm. So the idea is, let's assume that these are the activities here, and if you put them in a feature space, you cannot. I mean, this is a school basic example. You cannot separate, for example, these two activities. But the activities have this temporal behavior, right? They happen sometime. I mean, I'm walking, then I'm lying, then I'm walking again, and they usually happen sometime. And if you include the time component there, you can see that, I don't know, this was walking, and this is potentially another walking, and this is, I don't know, sitting. So this is a lightweight, in a way, online clustering algorithm that showed really, really interesting results, and it got media attention when I was there. I also gave some press conferences. It aligned well with some innovation festival that they had in Brighton. So this kind of titles in the media. I read this kind of titles the next day when I woke up. A new algorithm will allow smartwatches to learn and monitor your every move, which is not completely correct, but it's something that how media perceives research and AI in general. Simon Stankovsky is another student of mine. I'm his co-supervisor. Mitya is his supervisor. He's doing eating detection. So can you recognize what when the person is sitting, and also what kind of cutlery the person is using? And you can see that by some smart feature engineering and also some smart data selection here, which is a problem by itself. And here actually he is using deep learning, even though these are random forest trees. You can predict the whole day recordings that I don't know, I was eating using a spoon, a fork, a hand, and similar. And the other application, this is a huge data set. It's called SHL, so Sussex Huawei Locomotion Dataset. And I was working when I was in UK on this one. We were collecting it, and then we are organizing actually annual competitions on this one, which are part of the UKIM conference. So basically, we have more than 700 hours of smartphone data. All the possible sensor data that you can find in a smartphone is logged into this data set. And you have different kind of transportation activities, walking, run, bike, bus, car, train, subway. It is publicly available data set, or at least parts of it, because we are organizing competitions. So we cannot give access to the whole data set at once. And these are some statistics where the person, we have 3 people going around London, Brighton, one of them went even to Liverpool, collecting data with smartphones. Okay, so this is summarization of the publications on activity recognition. Okay, now let's forget a little bit about activity recognition and go for fall detection. So the problem with falls is that people fall. The older they get, they fall more often. The problem is that some of these falls require medical attention. So a smartwatch to call the neighbor or some service that the person has fallen. So what we did here, I'm not sure if I have enough time to show some of this, but this is me performing the fall. So we collect, again, data collection for fall detection is a problem by itself. How to collect good data using accelerometers here that later you can develop models. So this is fainting, like slowly falling here. Then you have jumping in bed. So this should give us a false positive if we rely completely on accelerations. So you define the problem, you collect the data, and then you perform all this kind of analysis. What sensor location is the best? What is the accuracy? How many false positives you will have? This is a binary problem here, fall or not fall. So this is a typical fall acceleration pattern. And this is what we are analyzing to detect the fall. And here you can see a lot of different approaches that we took while developing this fall detection. So algorithm that analyzes only this acceleration pattern, that analyzes some sensor orientation, if the person is moving or not, activities completely based on machine learning. So again, you equip the person with all these sensors, and then you perform the falls, and you get the data, and then you perform the data analysis, machine learning, rules, feature engineering. And this is one of the architectures that we used. So we had inertial data, the accelerometer, and also location data. So this system here gave us the 3D coordinates of the person. And we have here, this is activity recognition model. So this is a machine learning model which recognizes the person's activity, and this is input to this context-based reasoning here. So the activity, the location, the movement, threshold-based acceleration, they're all combined and using some intelligent reasoning to detect if the person has fallen or not. And this graph here shows that our system, I mean, that's the goal of every paper and every study, that your algorithm is the best. And here you can see that the green line achieves the best results, especially when during the falls. So these here are non-fall but difficult events, like, I don't know, falling into the bed, jumping into the bed, and non-falls normal activities. This is also a nice plot that shows how to combine the different inertial sensors and location tags. And you can see that using one inertial and one location tag is enough to have, let's say, around 97% accuracy or F1 score. In this case, it was accuracy. Then we continued with this study in the InLife project, which was a Horizon 2020 project, where we said, let's put this into a smartwatch. So to develop a prototype smartwatch that when a fall is detected, it will inform call service. Also, it will inform some web portal, which it will send an SMS, actually. The idea is to work, also the watch to work outside. And we did that. We developed the algorithm. It was, so we had kind of ready algorithm from 2011 or 12, when nobody was talking about smartwatch based fall detection. But and now we have Apple Watch, which sells this kind of fall detection algorithm as a really advanced feature, and it detects quite well, and the media coverage is amazing. So, but we had the algorithm even before that, but we were not kind of business oriented. So researchers are not good businessmen. So unfortunately, yeah, now Apple is dominating this market. Unfortunately for us. Fortunately for the society, we have a smartwatch that can detect falls and dial for help. This is a recent study done by Ivana Kiprianovska for her master thesis. So yeah, you can detect fall, but after it happens, after the person is injured potentially. But can we detect a risk factor of potentially the person falling? So it has been shown that for older people, they usually, before the start to fall, they have a kind of gait abnormalities. So we said, okay, can we use a smartwatch and accelerometer, especially accelerometer, also gyroscope and magnetometer, compass sensor, to detect if the walking is normal or abnormal. And this will be an indication that fall will potentially happen. And this was also a really nice study that Ivana did in a few months. I was positively surprised by her work ethic. And she showed that it is possible to detect normal and abnormal walking with approximately 90% accuracy with using some deep learning architecture. Here, I mean, you have the paper here. You can always go and check the details. I have two more case studies. I'm aware that I'm running out of time, so it will be quickly going through them. But if you have a question, please feel free to ask. The next one is, can we detect how many calories I'm burning during the everyday activity? So it was a natural continuation of the activity recognition. So using wearables, a smartwatch or whatever, can we detect how many calories I spent during the sitting exercise, walking, cycling, or whatever? And this is actually a machine learning model or a regression model at the end of the day. This is the architecture that we proposed. This was the core of my PhD thesis. It is context-based ensembles of multiple sensors. So how to combine these different sensors in a context manner in order to better estimate about the user, in this case, about the energy expenditure. And of course, we showed that our proposed algorithm is the best. We did a thorough evaluation here. We compared to some devices that are present in the market. So here, the lower is better. The ensemble is our approach. Now, the final thing that I'll talk about is the next step. Can we detect the arousal, the valence, positive or negative feeling that we have for something, or the stress of the person, or the expressions that the person is making, smiling or whatever, using again wearables. So again, machine learning model to recognize all these different states of the user. So yeah, PPG it's a sensor that measures the heart activity. IMU is the accelerometer gyroscope. EMG is a sensor that measures the muscle activity. EDA is a sensor that measures the sweating rate, how much the person is sweating. And eye tracking, I'll mention why it is interesting. This collaboration that we have with MTech Labs, it's a UK company that is selling this mask, which can be worn on the face, and it is installed on a virtual reality device. And actually, you have also input from the eye tracking if the virtual reality device has this option. Let me first start with the stress. So to detect if the stress is low, medium, or high. So I will not go into the definition of the stress. It's a problem. There is no strict definition of what is stress. And that's why it's even more challenging to detect compared to activities or energy expenditure and similar. So the ground truth is kind of not perfect in this scenario. And also the results are much, much lower compared to activity recognition. So this is one study that actually Martin, my brother, has designed. And this is me solving some mathematical problem, and he's timing that. And there is also a reward motivation behind the study. Why? Because people are more stressed when they compete. So it's a competition. Who will finish first and most accurate, that kind of thing. And we are wearing all these different sensors even on my head. Some wristband here. Also, I think we have a Zephyr sensor on as a chest strap. And you are measuring all these sensors that I have mentioned. And at the end of the day, you want to combine them somehow through some machine learning, some context-based architectures or whatever, and to recognize in real time what is the stress of the person. So automatic monitoring of the stress of the person. Here we have some interesting results, which look nice, but in reality, or in more not that lab scenarios are difficult to achieve. So the accuracy is around 60-70%. Yeah, finally, I'll mention again the MTech Labs. They are producing this mask. We are developing right now with Ivana and Simon. And Martin is also helping there, how to recognize the expressions of the user. So basically, most of this sensor here has a sensor that measures muscle activation. Using this muscle activation, you can recognize when the person is smiling, frowning, surprised, neutral state, and similar. And actually, I have, to conclude. So you should be aware of what's wearable computing, how machine learning is used in wearable computing, activity recognition, fall detection, calorie expenditure estimation, stress arousal balance is the next big thing in which there is a lot of activity in the research community. And my final slide is to thank all these people. So it's not so that I've done this all by myself. Of course, my supervisor for my master and my PhD thesis, Matthias Gams, my co-supervisor, Mitja Lustrek, are the special people there from the Josef Stefan Institute that helped me a lot to achieve all these interesting studies and which show me the way in this wearable computing or ambient intelligence or intelligence systems in general. And a lot of people, so Stefan is also still there, Bostian, Simon, some people from the University of Sussex, which I collaborated during my postdoc. So Daniel Rogan was my supervisor, Matthias, Lynn, Javier. People from now, from my faculty, which we are collaborating on the WideHealth Project, Maria, Daniel, Valentin, Dimitar, Anna, Emilia, Bojana. My brother Martin, which is amazing researcher, especially in this stress area, arousal balance. He is currently in Università della Svizzera Italiana. Idea Lab is the startup that we have, and together with Ivana and Simon, we are doing this amazing research for MTech Labs, where we are collaborating with Charles, Bram, Ify, John, Milky. So that is all from my side. This is my email. If you have any questions, you can ask here or through email.
Thank you very much, Hristijan. And I think now we have time for questions, and I would like to open the floor for questions. So does anyone have a question? You can just open the mic or raise your hand. And
come on.
well, I'll ask one while people are thinking about it. So one of the things that you said was that getting to the feature table is the most important thing, and the hardest one, and also that obviously to get there, you need to get a good data set. So one of the things that we saw your videos like jumping or fainting to the couch. One of the things that we are seeing is that also a major difficulty in having data sets that are well annotated and that have real life data. Maybe these companies, so we know that companies like Google and Apple are being able to get more data than maybe the occasional researcher. And so my question here is, if you feel that this is also one of the major issues, so how can we find better methods to get data sets that are representative of real life and more complex? And if you have any ideas on how we could even use these other sensors and other approaches to get to those data sets.
So, okay. First with the Apple Watch. So right now they sell millions of this device and they actually collect data. It's quite easy to get good true positive full or false positive. I mean, the user will tell you, and they'll improve with time. And sometimes actually you should be brave enough and say, okay, I'll release this to the beta testers or whatever, but I'll also ask for some feedback. That is possible for false, because the user will inform somehow Apple, this was a false alarm, please do not do this in the future. So some kind of active learning with your users. But for the activities, it might be tricky. Orhan, which is part of our project, it has interesting idea, which we also had back in 2016-17. We are proposing this kind of project. Can I create a virtual simulation of a user performing the different activities? And it is possible to do that, right? And you can also measure the accelerations of the different limbs of the hand, of the leg, of the foot, or whatever, and use these virtual accelerations recorded in a virtual reality to train a model that will be applied in a real world. I mean, this will be amazing, and it is possible, especially for the accelerations. You can, they will be using these simulation tools. You can achieve that, and I hope that Orhan will have some advancements in this field. And it will be nice to see how this ends. And another thing is transfer learning, deep learning. It's really not that well exploited in this area, wearable computing, because it does not work from the beginning as it works with images. So can you combine different data sets? Can you, and because there are lots of different activity recognition data sets, I don't know, maybe 100 or something like that, but they have all their specificity. Model trained on one will not work on another one. So these are my thoughts on this subject.
Thank you. So do you have more questions? Any doubts? Any?
Let's give a few more seconds. Usually people are shy. I can ask some of the people that I have mentioned in the.
Okay, I will join the conversation.
Oh, great.
Hi, Hristijan.
Hi.
I would like to ask one question about the commercialization of the algorithms. You mentioned that now you're working on algorithm for stress and detecting this kind of algorithms. Is there any commercial algorithm right now? Because as far as we know now, Apple is introduced, or actually it was introduced in the past, this fall detection algorithm. Is there any commercial algorithm that we can find right now for detecting stress, or I don't know which was the other four?
Yeah.
Let's focus on stress.
I'll cover them. Yeah. So thanks for the question. The short answer is yes, there is. So I'm not sure if Apple has stress detector, but for example, Garmin is having this service. I think some of the Samsung smartwatches are detecting also this one. But the problem is that with stress, it does not work really well. And with stress, you are entering in this medical domain. And I'm not sure how these algorithms will be accepted by the public. If it detects wrong stress, it will make you even more stressed, even though you are not stressed. So all these algorithms, which are kind of analyzing the heart activity data, have their ethical problem of accepting from the people, from the audience. But we'll see. I mean, stress detection, arousal valence, it's a new area, even though there are commercial applications, but they are not perfect, and the accuracy there is really low. So there is a huge room for improvement.
Okay, thank you, Hristijan.
I can ask a more technical
Another question, Daniel?
Yeah, about the rotation matrices. Where do you use it? In which phase? In the pre-processing phase, or during the detection phase? I'm not sure about that. Maybe you can add some more details on that part. How do you use the rotation matrix?
In the pre-processing phase.
Processing. So you
before the feature extraction.
Okay.
So you are correcting the orientation of the sensor virtually before you do the feature extraction. So your features in the training set are like for sensor orientated like this, but in the real life it is like this, and you can detect what is the angle between this and this. And once you detect it, you can rotate the data. And you do this before feature extraction.
What if you take the time into account? It changes the rotation during time.
Yeah, so that's another issue. In our experiments, we assumed I have a calibration phase when I detect when the person is, I don't know, sitting, and then I say, okay, I'll calculate the inclination angle and then rotate all the sensor data from this point on. But you're right, this can change. So it will have to probably recalibrate after a while. And there are ideas how to do it. So on every sitting activity, you recalibrate. On every standing activity, on every still activity, you recalibrate.
Yeah, like an adaptive.
Yeah.
Okay. Thank you.
But it is a really cool idea.
Yeah. Thank you.
And it's not that well exploited in practice.
I have some ideas we can probably discuss offline here. Thanks.
Thank you.
Do you have more? I have one.
Yeah.
And when you're talking about considering time to distinguish between classes in the walking, sitting, adding another dimension, so you consider time, but you don't. Do you consider the possible sequence, like a chain of events between those classes, or not? So they are independent, those classes. So I don't know if I'm
for example, you cannot go from walking into lying
without going through
directly, without going in something as a state machine. Actually, we did a lot of hidden Markov models for this.
So my thoughts.
So to define the state that you, in order for you to go from walking to lying, there has to be a transition and that kind of stuff. And that is, sometimes it gives some improvements. So it is used as a post-processing step. So you recognize in real time, and then you say, let me correct a little bit. Because usually it happens walk, 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 then stand, stand, walk, walk, stand, stand, if it's on a second interval. But those standings are actually walking. I mean, in theory, in practice, they can be standing. I'm walking a little bit, and then I'm kind of standing and continuing, but they are labeled walking, and your machine learning model is expecting walking. So this is also a problem with the labels. And hidden Markov models and those kind of methods that use this state can correct those small issues. But the complexity that it adds on the method sometimes is not worth it.
And I would say that some deep learning approaches will already look at those kind of transitions, right? Because they have some memory.
So this conf LSTM architecture that Rogan suggested in 2016 is using the LSTM. So the idea of adding the LSTM was that there is a time continuum with the activities.
Yep. Good. Thank you. Nina.
Hi.
Hello.
Hristijan, thank you.
Hi.
Very interesting. I will just pick up where Daniel left off, I think, with the rotations. So
you're the expert there. So any input from you is welcome.
Yeah, this is what I was wondering. So in case, of course, that you have this pure gravitational acceleration, it is very direct how to get the angles. But in case you don't, so you only have the gravitation, I mean, just the acceleration direct.
The linear
sensor.
acceleration.
Yeah, or not the linear, just what you get directly from the raw acceleration. How do you deal with this? Because the acceleration sometimes wears much more information than just the angles, with some fast movements, with some, I don't know if I made myself clear, because this is something, so how do you deal with this?
So in the raw accelerometer data, you have the gravity. So by default, you have the gravity.
You have the gravity and something else. So something else. So how do you deal with this something else? This is.
Yeah, that's.
Do you? I mean, you probably. I guess it's. I mean, is it there's some low filtering done or on the acceleration? Because we also did this. I know that with the SHL, you actually provided even the quaternions and everything. But with when you get the raw data, it's sometimes, I don't know. So we usually also go with the acceleration, but I guess some sensor fusion at this point, combining with the gyroscopes or something, is maybe a good thing to be done, because the acceleration sometimes wears just a little bit more. So when just rotating directly from acceleration, it could be just a little bit, So.
It's a problem. I haven't investigated in so many details. I've done it only on the accelerometer signal. And when I was doing that for my master thesis first, it was not as simple as it is in theory. The results were not as I expected, and I can assume it's the reasons. Some of the reasons you have mentioned them now. So it's something that it has to be further researched.
Further.
Yeah.
No,
Yeah.
thank you. But it was really interesting. So thank you.
So I think we are wrapping up, and let me thank Hristijan for the presentation and for presenting all this wonderful work. A lot of, well, I don't need to tell, but the words that you want show that the work is indeed relevant. So we are continuing with these seminars, and so I welcome everyone. You will receive well, the announcements of the other seminars, and you can check the WideHealth webpage for other events that we are organizing and to engage with what this consortium is doing. Thank you for coming, and see you next time.
Thank you for coming to the seminar.
Yeah. Also, these sessions are recorded, and we publish the videos on YouTube and also a podcast, and so you can get to them through our webpage or social media webpage. So thank you and good afternoon.
Bye-bye.